Let's now talk about how we can define the heights of the tree recursively. And we already walked through the basic definition for the heights. Let's see just more algorithmically about how it can be defined. So given a node, the height of the subtree rooted at n will be defined as, and just notice that any node can be passed as input. We just calculate the height just for that particular subtree rooted at the input node. And the base case would be if n is simply just a leaf. In that case, the height would just be 0, right? If the node is simply, for example, at the bottom of the tree, in that case, the node has no children, the height would just be, by definition, simply 0. We talked about it also when we actually visualized the definition earlier. Otherwise, it's going to be 1 plus. And over here, I'm going to visualize this part as well, but just remember the 1 plus over here is really go from the node to its child node. That will be the one edge we have to compute. Similar to when we actually say 1 plus the depth earlier, so the 1 over there is really from the node to its parents, right? You can see that's kind of symmetric. I'll visualize this for you as well. But it's going to be 1 plus the maximum heights of all the subtrees rooted at n's children over here, right? So that's the very simple definition over here. Just two cases, base versus recursive. Just one case for each. And let's now go over the Java code, and we're gonna talk about some unfolding for tracing as well. Right, so that's the Java code over here. So we got the heights, which will take any arbitrary nodes, and notice that, for example, these nodes over here are external, in which case the height by definition would just be 0. So when the children, which is the array, the length is equal to 0, in that case it's going to be simply just 0. Oh, by the way, so you can see the first line over here, we'll simply compute the children of n over here. So n dot get children. And you can definitely see the definition for get children in the source code. I'll leave that study part to you. And so this will be the base case, simply 0. For example, Ernesto, Shirley, Vanessa, Peter, and Anna, they don't have any children. They're simply external nodes. In that case, their height will be 0. Let me write it down over here. If children.length is equal to 0, that means n is external, or a leaf. Alternatively, you can say it's a leaf. And for the recursive case, we simply calculate the heights for every child node. For example, we know that David is not external, it's internal. In that case, we'll simply calculate the maximum heights of each, we'll simply calculate the heights for each of its child nodes and then choose the maximum. That's what we'll do. Similarly, in order to calculate the heights for Chris, in that case, we have to calculate the heights for Elsa and Anna. So because Chris has 2 children over here, and then choose the maximum heights among Elsa and also Anna, and similarly for other and etc. for other cases. Alright, so this part here, I'm gonna let you study the code, but for this part over here, you can see we are making recursive call over here. Let me show to you the recursive call. You can see we got heights over here, and you can see we just try to call the heights on every child. So this is a strictly smaller problem to calculate the heights of one of the child nodes. So this is a strictly smaller problem, which is to compute the heights of, rather than the root node, is going to be one of its child nodes of a child node. Right? This is definitely some recursive call over here. But you can definitely study the code yourself and then reach out to me if you got any trouble. Let's now try to talk about some unfolding, which will be interesting to do just to make sure you understand the recursion more deeply. Alright, let's still use this family tree over here. And you can definitely look at the test case, which is also included in the source code, and I will assign some exercise to you a little bit later. But you can definitely see for the external nodes, all their heights are zeros. On the other hand, for the internal nodes, their heights will be at least 1. Alright? Let's now talk about the tracing for this. Let's say we try to calculate the heights for quiz. Let's say we start from here. Alright, over here. So by definition, it is going to be equal to, so we want to reach out to each of its child nodes. So we're going to go to this one over here, and we want to go to this child over here. Each one of them will be just one edge. So that'll be the +1 they're going to watch out for, right? It's going to be 1 plus the maximum. Right? For the maximum, assume that's exactly the calculation over here to calculate the maximum using a loop. Right? It's going to be for the maximum. Let me just use the utility. Just use this one here. Let's say it's going to be the maximum of. We have two children of for quiz. Either it is Elsa or it's Anna, right? So this will be Elsa over here, and this will be for Anna, right? Either one. So it's going to be the heights of Elsa and also the heights of Anna. And are we done? Actually, not yet, because you can see for Elsa, Elsa actually got further children to really calculate their height, so we should really go further. However, for Anna over here, it's done because Anna is actually external. So we know that by definition, the height for the subtree rooted at Anna will be simply 0. Let me use a different color here for Anna. It's a terminating case. So why don't we use why don't we use green in this case? So let me use green over here. So Anna over here is going to be actually just this part here. Alright, so for Anna, it's actually 0. So for this part over here, by definition, it's a base case because Anna is external node. Right, let's now go further. We need to calculate for the heights for Elsa. But let me just lay out the structure. It's going to be 1 plus over here. And then we still got our maximum calculation over here. And we know that it's going to be a little bit bigger over here. Right? So the heights for Anna, we know that it's actually 0. Right? I'm going to put 0 over here. What about the heights for Elsa over here? Right? In that case, we have to actually go over. We have to go over to the individual child nodes. In that case, let me just be consistent with the color over here. So we're going to reach out to the first child, the second child, and also the third child over here. Right? Each one of them contains one edge. So that'll be 1 and 1 and 1. For the heights of Elsa is going to be, first of all, the 1. Right? You can see that's the 1 edge going from the root to one of its child nodes. So that'll be 1 plus. And then by definition, it's going to be the maximum of the heights of that particular node's children, which will be Shirley, Vanessa, and also Peter. Let me box them. Let's say pink. Shirley, Vanessa, and Peter. And how do we write it out? It's going to be plus the maximum of the heights of these 3 child nodes. And of course, we're talking about specifically the subtree rooted at Shirley, the subtree rooted at Vanessa, and the subtree rooted at Peter. Let me write it slightly more briefly. So it's going to be the heights of Shirley, okay, and also the heights of Vanessa, and the heights of Peter. And if you actually look into the slides, I actually got the complete writing, but just for illustration, I'm sure you can still follow. Right, so that'll be the maximum, and don't forget about we also got this outer parenthesis as well for this maximum, right? And we are basically done because you can see each one of these 3 child nodes, they are simply external, meaning that by definition, their children length will just be 0, meaning that they're going to have 0 heights. For each one of them, it's simply just going to be 0. 0 here, 0 here, and also 0 over here. What's the maximum of 0? Simply 0. 1 plus 0 is going to be 1. What's the maximum of 1 and 0? Is going to be 1. Right? The maximum over here is simply just 0. 1 plus 0 is going to be 1. What's the maximum of 1 and 0? Is going to be just 1. And 1 plus 1 is going to be equal to 2. So 2 will be the heights of quiz. And you can definitely see this test case over here. You can see for quiz, his height is simply just 2. That's one of the test cases I got for you. You can definitely just make sure it's actually working, right? And this tracing is slightly more complicated than the one we did for the depth. And you definitely want to practice this, right? Let me just suggest another tracing that's slightly more complicated than the one I did as exercise for you, right? Just don't forget you got a comma over here. What about we do this as exercise for you? What about we start with David? How do you calculate the heights of this largest subtree? Do the exercise. I think that'll be very worth for you to actually unfold the recursion. That's really the main point I would like you to really try to get used to. This will be the exercise for you. All right. Exercise will be to unfold the recursion, like how we're doing over here. Alrighty, so now we are finishing discussing the two utility methods. I think that will be a very good starting point for you to really see how things will work recursively on the tree nodes or the tree. Let's now go back. I think this one has been discussed thoroughly, especially the test cases, and don't forget about the exercise. And this will be this is the unfolding we just did, right? It's just written in a more precise manner, but I think for the one in the illustration is rather complete as well. And two more exercises for you. You can definitely reuse the structure of the code we got over here. You will just have to add in some more utility methods. That's what I want you to do, right? So what methods do we want you to exercise? One will be, given a node, I want to calculate all the ancestors for that particular node. Return that as an array. For example, let's say if I give you the node of Vanessa, in that case, the array that's returned should contain Vanessa, Elsa, Chris, and David, right? And the second method to exercise will be to calculate the other way, the descendants. For example, if I give you the node Vanessa, in that case, the descendant should really contain just Vanessa herself, and because she has no children in this case. What about if I give you, let's say, Chris? In that case, descendants will be Chris, Elsa, Anna, Shirley, Vanessa, and Peter. So these are the two exercise methods I would like you to complete.